So brown dwarf stars, as we should properly call them, are a very interesting class of objects that we had theorized about until the last few tens of years when we've begun to make some discoveries. So just a brief recap about stars. Stars are giant pressure cookers carrying out nuclear fusion in their cores, fusing hydrogen, the first element, to helium at tremendous pressure and temperature deep inside the core, and then the heat carries the energy away and radiates away from the surface. See the stars in different colors when we look up in the night sky, and the color is a direct reflection of their surface temperature. It also is a reflection typically of the mass of the star. The more massive a star is, the greater the internal pressure and temperature in that nuclear core, and so the faster it carries out the nuclear fusion process. The nuclear fusion process is very sensitive to temperature. It increases with the fourth power of the temperature. So if you double the temperature, you will make the fusion happen 16 times faster. It's a quite incredible relationship. And so more massive stars have the color going with the temperature, as shown here. We've got a few examples with the sun in the middle with a surface temperature 5,000 or 6,000 degrees and a yellowish color. Cooler than that, you have orange or red colors for the surface, and hotter you go white hot or even blue hot for the colors of the stars. Now, the smallest types of stars are these little red dwarfs, as we call them. We would call our sun a yellow dwarf, but a red dwarf is even smaller and cooler. And they are the most common type. Around about 3/4 of all stars are these little red dwarf stars. Nature manages to make many more small stars than big ones. It's much easier for it to get enough material together. So here's a little comparison of the size of a red dwarf star against a picture of our sun, busily having a solar flare there on the right, taken in the ultraviolet light, that one is. But nevertheless, a yellow looking colour and a red looking colour to the surface of these stars. And anything that's less than half the mass of our sun, we would call a red dwarf, as long as it's at least 7.5% of the mass of the sun. Between those ranges, so between 7.5% and 50% the mass of the sun, the stars do get hot enough to form the temperature you need inside the core of the star, which is 10 million degrees, in order that nuclear fusion can be carried out properly. And so below 7.5% of the mass of the sun, it doesn't get hot enough in there to trigger any of the normal nuclear fusion at all. So these red dwarf stars are the smallest type, and they range from 7.5% to 50% of the mass of the sun. The ones from 50% upwards, we see those as orange, and we call them orange dwarfs. So I referred to nuclear fusion going on in the center. This is where hydrogen is combined in a number of stages to form the next element, helium. And the first stage is to smash two of these little red dots, the protons, the simplest particles, together to make a two-particle nucleus of deuterium. That's a heavy isotope of hydrogen. Then you add a third particle in, and you get a three-particle nucleus, which is helium-3. And you smash two of those together, and you get helium-4, and you get two of your protons back. So you used 6 protons, and you got 2 back, consuming 4. So the 4 turned into the one 4-particle nucleus. The blue particles are neutrons, and this process requires the ability of a proton to turn into a neutron, but that's not really the whole topic of this talk. Just want to give you an overview of the process. And the fact is that you can't get that first step to work of taking the two positively charged protons and combining them together until you get to 10 million degrees. And this is because they're both positively charged and they will repel each other furiously through the electrostatic repulsion of like charges repelling. And so you have to crash them together very hard indeed in order to get that first step to happen. And each little step there, you get a flash of energy coming out. And it's that energy that powers the stars. So here's a very famous little red dwarf star, Trappist I, famous because it's got 7 planets, all of which look like roughly Earth-like planets around it. But the star is almost as small as a star can be. It's just 8% of the mass of the sun, the limit being 7.5, as I've said before. So much smaller. If there'd been a little bit less mass around when it was forming for it to feed up on, then it would have failed to become a proper star. It would not have lit up fully as a red dwarf. It's about the smallest star we know that's actually properly carrying out that nuclear fusion in the middle. So what would have happened if it had been smaller? Well, here's a picture I took of Jupiter, and very nice image with the red spot and the cloud belts and so on. But Jupiter is, if you like, a failed star. It's made of the same stuff that stars are made of, 75% hydrogen and 24% helium, a little bit of other stuff. But it's only got 1/1000th of the mass of our sun. So you would need 75 Jupiters to reach that 7.5% limit and become the smallest possible proper star. But Jupiter does give out some heat. We detected this back in the 1960s, that Jupiter gave out more heat than it receives from the sun. And that energy that's creating that heat is caused by the contraction of its inner core, falling inwards under gravity still. And any planet or gas giant like this that forms will have a lot of heat left in it when it's originally formed as a result of falling inwards under gravity and forming the planet in the first place. That's why we have a molten core in the middle of the Earth. Plus, there's a lot of stuff in the Earth that's radioactive, that's trapped, and there'll be some of that in the 1% of Jupiter that's not hydrogen or helium. So 2 sources of energy in the middle, keeping it a little bit warm at around about 125 degrees above absolute zero. So cold really, but slightly warmer than the cold of space. So there are probably these objects that are between the size of Jupiter and the size of the star. We've certainly found planets around other stars that are gas giants bigger than Jupiter, maybe 10 or 20 times the mass of Jupiter is not uncommon. And these sorts of objects are these failed stars that form that missing link. And here's the first one that I wanted to show you as a real system rather than the artist's impression. And this is in a star called GQ Lupi in the constellation of Lupus the Hare. And it's an orange star, a K-type orange star, so only 70% the mass of the sun for the main star. But its companion there, labelled B, was imaged in 2005, orbiting around the main orange dwarf star at 100 astronomical units, so quite a long orbit, much 3 times as far away from its star as Neptune is from the sun. But it's quite a big object, too big really to be described as a planet. It's 2.6% of the mass of our sun, or 26 Jupiter masses if you prefer to measure it in terms of how many Jupiters it is, so a lot bigger than Jupiter. And most recently they found that this system's even more complicated. They found a more distant red dwarf orbiting around outside 2400 AU, but that's just beside the story really. Here's another one. This is Gliese 229b, the little tiny bright dot. The main object is Gliese 229a, which is a red dwarf star in itself, and 229b orbits around it, directly imaged here by the Hubble telescope, and is between 21 and 52 times the mass of Jupiter. So up to about 5% the mass of the Sun. Still too small to be carrying out that 10 million degree temperature fusion in the middle of its core. But it is, in fact, quite warm, and it has a surface temperature of nearly 1,000 degrees Kelvin, 950 K. So enough to be glowing very strongly in the infrared. And it is, of course, an infrared image that we've used here to pick it up. So where is all the heat coming from that's keeping that so warm? Well, turns out that above 13 times the mass of Jupiter, the core temperature can reach 1 million degrees. Not the 10 million that you need for the first step of nuclear fusion, but enough to trigger the second step. And so the small amount of natural heavy hydrogen, deuterium, that might have been in the composition of the object in the first place can fuse with and will fuse with ordinary hydrogen and release nuclear energy as the second step and form helium-3. And so that second step is enough to warm up these, and I will call them brown dwarfs now, because this is what we now deem to be the limiting factor for a brown dwarf. It must be at least 13 times the mass of Jupiter and have a core temperature of 1 million degrees or more, or have had that temperature at some point, sufficient to trigger this limited deuterium fusion in the middle. Now, there's not a lot of deuterium around. Only 1 in 10,000 hydrogen atoms from the Big Bang was formed that way. And so it doesn't give it a huge amount of fuel, and they burn through their deuterium fuel quite quickly, but it does heat up the core. And so we would now fill in the missing link with these brown dwarfs. Anything from 13 times the mass of Jupiter to 75 times the mass of Jupiter is a brown dwarf. 75 and above is a star, starting with red dwarfs, and then, not shown here, orange dwarfs, which go from about 500 times the mass of Jupiter up to around about 800 or 900, and then you get to the yellow dwarfs like our Sun. So these are the missing links in the chain. And if you remember, I said there were a lot more red dwarf stars than there are of the larger stars. And so it sort of figures that nature would probably have made a terrific number of these brown dwarfs if it finds it easy to make smaller objects and harder to make big ones. You can imagine that there must be a lot of these brown dwarf stars out there. Well, here's another interesting one. It's in the Pleiades Seven Sisters star cluster, just 420 light years away from us. And it weighs in quite massive at 5.5% the mass of the Sun, 57 MJs, masses of Jupiter, and has a surface temperature at, well, 2,600 degrees Kelvin. That's really quite hot. It's almost going to be glowing into the red, but not quite. It's going to be putting out its energy in the near infrared part of the spectrum. And the reason is it's carrying out another nuclear trick. It's actually managing to use the element lithium. And what it's doing is taking that lithium, crashing it with protons, the ordinary hydrogen atoms, and splitting the result into 2 helium-4s. So it's destroying the lithium and turning it into a pair of the heliums there. So you start with a 7-particle nucleus and a 1-particle nucleus, and you end up with 2 4-particle nuclei. It makes huge sense. And normal stars also do this. They burn up all their lithium and destroy it very rapidly. But it turns out that Tade 1 is just above the 5% mass of the sun limit, where the core temperature gets to 2.5 million degrees. And this creates a lithium fusion trigger inside the brown dwarf. So they get an extra burst of energy. They don't just burn the deuterium, they also burn up the lithium as well. And so we are discovering that there is more than one type of these brown dwarfs in there, depending on exactly how massive they are. We've also found a third category, the ultra cool brown dwarf. And these are ones where they seem to really have quite low temperatures. So this one's only 500 degrees Kelvin, a little bit of warmth there, but not a huge amount. And so we can do a little addition to our diagram now. We've got the sun-like stars. We've got Gliese 229a here, a red dwarf. Tade 1, one of these lithium brown dwarfs. Gliese 229b, a deuterium fusing brown dwarf. And then we've got the ultra cool Visa 1828, only 500 degrees. And then Jupiter. And these images are actually to scale. The size of these objects doesn't increase very much as they grow in mass from Jupiter upwards, because you add mass and what happens is gravity crushes them to a greater density and heats the core up a bit more until you get the nuclear fusion starting to kick off, and then that provides the extra heat for things to swell up and form a much larger stable structure. We're actually beginning to study these brown dwarfs, and there's one here with a thoroughly unpronounceable name that they've even detected as having aurora within its atmosphere. So quite incredible that what we're actually able to measure these days, the northern lights on a brown dwarf 20 light years away. We found some brown dwarf binaries. Lumen 16 here is a pair of brown dwarfs orbiting around each other, and there's several other images of 4 other brown dwarf binaries. Again, our sun is unusual in that it does not appear to have a binary companion. Almost all other stars tend to be in 2s or 3s or groups. The single stars are quite rare. We also found brown dwarfs with dust disks around them. We think a dust disk is the origin of the planets in our solar system. The early sun would have had a dust ring around it, left over from its formation, and out of which the planets were born. And we think there's no difference really with smaller stars. We saw that Trappist I had got a family of 7 planets. Indeed, here is the idea that brown dwarfs can exist with dust rings, and even we think in this image here we've detected a planetary companion to a brown dwarf in the image there. And I think the best image is this one, which was the first image of a planet outside of our solar system. The whitey blue object is the brown dwarf, and then it has a planet B orbiting around it, which is only 8 times the mass of Jupiter. So it's a little system in its own right, 40 light years away. And the ratio of the masses between the main object, which is this brown dwarf, and the Jupiter-like planet is only 3-to-1. So quite incredible mixture of different types of systems. Okay, so what about the habitable zone of a brown dwarf? We have a habitable zone around our star. We live in it. That's probably a good job. Where it's not too hot, it's not too cold, it's just right, the Goldilocks zone. And all stars have that, and we are very keen on finding planets that live within the habitable zone of their stars. Now, a brown dwarf, it's giving off some heat, but it probably doesn't give off heat for very long at a stable temperature. If there is a burst of nuclear fusion early in its existence, that'll soon run out of fuel, and then the star will be doomed to cool over time as it's not releasing new energy in the center. And so the habitable zone around it will narrow and shrink. You'll have to keep getting closer and closer to it to get enough warmth to keep any water liquid. And so I'm not sure that these brown dwarfs are necessarily the perfect candidate for looking for any sort of life on planets orbiting brown dwarfs. There's another possibility that some of these systems may contain planets of a rather unusual type. That we've not discovered any of these yet, but the hypothesis is that you could get carbon planets around brown dwarfs that would be very dry. The water would be driven away by all of the initial burst of heat and locked up out in a sort of mini Oort cloud of icy cometary type objects, but without any giant planets to then change things and disturb those comets to fall back in. The water wouldn't be re-delivered, as it probably was on Earth, back to create oceans, and so you'd find that your planet would have a very much larger percentage of carbon compared to oxygen, because it wouldn't get the water re-delivered back as H2O. So we're very interested in looking to see if we can detect the signature of any of these carbon planets. Now, I mentioned that the Sun was a sole star, doesn't appear to have a companion, and the question, I suppose, is could it have a brown dwarf companion that we failed to spot due to it being rather faint and dim object? We might have overlooked it. Well, I think the answer is no, because we've done fairly extensive surveys. But there was a theory kicking around at one point called the Nemesis hypothesis, that maybe the 26 million year pattern of extinctions that we seem to see in the fossil record might be because we have a companion red or brown dwarf orbiting the Sun in a very long, thin orbit that's currently a long way away, and that might periodically disturb objects in the Kuiper belt and hurl a shower of comets our way, and cause the mass extinctions on the Earth. We've looked very, very hard for this object using infrared telescopes that should be able to see anything, even a cool brown dwarf, and the range of possible sizes for such an object and distances is definitely going down and down all the time. So we're pretty sure it's not there, but we haven't managed to rule out every possible scenario yet.